and I've been doing work on glass and glazes for some time now. Glass is a different material, obviously, from ceramics. And what you've got to remember about it, whereas with ceramics, we shape them when they're cold and then fire them so they're hard, glass is shaped when it's hot, and it's hard when it's cold. It's brittle and it's transparent, as you know, and it can be blown, just like gum. And then you cool it, and you've got the shape you need. Now, the main component of glass is silica, or quartz, SiO2. We're familiar with sand, which most sands are very rich in silica, and sand is often a good raw material for glass, but also we're used to quartz crystals, which you can see in New Age shops, mineral collecting shops, and so on, dealers. And it's all the same material, all the same chemical composition, as are the white quartz pebbles you can find on the beach. They're also made of silica, and they were quite popular as a starting material for glass in some parts of the world. Now, the problem with using this as a raw material is that actually it melts at 1700 degrees centigrade. That's hotter than you get in a modern steel refinery. And a Mediterranean pottery kiln will maybe take you to 1000 degrees centigrade. Even a Chinese porcelain kiln will only go to 1250 or 1350 degrees. So you have to be able to melt the silica. And what the glass makers did to melt the silica was to add something called a flux, which is a substance that lowers the melting temperatures of other things. And so here you can see what goes on. If we just try to melt our raw material, our sand, to make glass, we'd need very high temperatures, which were beyond the ability of the traditional glass maker. If we had a flux, we can melt it at 1000 degrees, which is not so different from the average pottery kiln in late Bronze Age and later societies. And of course, glass making really started in the late Bronze Age. It's a relatively recent material, glass. You have to bear that in mind. So this is the typical sequence for making glass, if you like. First of all, you need your source of silica, which is could be sand or it could be a quartz pebble. Then you need a flux. And the earliest glass makers, and indeed people in the medieval period, burnt plants to make their flux. They took plants from, in this case, from saline environments in hot countries, by the coast in the Mediterranean or in the desert in Syria. They burnt the plant and they got ash. They mixed that with the sand and then they could melt it in a furnace. And so the first flux we have, and there are 3 flux types which I'm going to talk about today, and I'll go through them. The first one is plant ash. This is on the beach just near Alexandria in Egypt. And this will give you an ash rich in sodium, which is a good flux for glass. But there was another flux which we're familiar with from antiquity because Pliny tells us about it. And this is sodium carbonate from Egyptian soda lakes, a place called the Wadi Natrun and in the Delta. And here you can see a lake which is drying out in the spring. This slide was taken in March. And you can see that round the edge of the lake is a white deposit, just there. And that's sodium carbonate, which is precipitating from the lake as the lake evaporates in the spring. And by the time you get to the autumn, the end of the summer, you can cut this material out in blocks the size of paving slabs. And that's a good flux for making glass. And Pliny tells us that natron, which is what he called this material, and what we still refer to it in ancient glass studies today as, Pliny tells us that this was the favoured glass-making raw material of the Romans, the favoured flux. Now, the third flux is the one used in medieval Europe, and that was based on burning wood from forests. either hardwoods like beech or oak, or fern, bracken, which grew on the ground. And unlike the last two fluxes, which gave material rich in sodium, this gives a flux rich in potassium. And so we have two types of glass, one rich in potassium, one rich in sodium. The Roman and the Bronze Age stuff and the Near Eastern stuff is rich in sodium, whereas the medieval European stuff is rich in potassium. So here we are. Here's an experiment by a colleague, Caroline Jackson, who's actually burning some wood in dustbins in a garage there in order to produce some ash. And you only get about 1% of ash in weight from a kilogram of wood. So you have to burn a lot of wood or a lot of plant to get the ash to make glass. Plus the fact, of course, you're having to heat the glass to melt it. So it's a very expensive material in terms of the raw materials used. And there's a change in raw materials with time and with place and with culture. And here I show you a graph showing the potassium and magnesium contents of Roman glass and late Bronze Age glass from Egypt. And you can see that the late Bronze Age glass has higher potassium and higher magnesium than the Roman glass. And this is made with plant ash. Plant ash is relatively impure. It puts impurities in the glass so we can recognize when it was made. The natron used by the Romans is a much purer form of soda. And so natron glass is very easily distinguished from plant ash glass. And that's how we know that Pliny was basically correct. What he told us was correct. Okay. And here are the glass compositions of these three groups. You can see you've got the Roman on the left-hand side with the low potassium and low magnesium, just there. Then we've got the late Bronze Age or the Islamic stuff, which is made using plant ash from the Near East, which are rich in soda. So we have soda, lime, silica glass in these two groups. And that's the same type of glass that is used in our windows and our bottles in the modern period. The composition hasn't changed very much. You can see the difference between the two of them in terms of these minor elements down the bottom, but actually the composition is not so different. The medieval composition, on the other hand, is very different. That's a potash lime silica glass, and that starts in around 1000 AD or that sort of time, and is made from the forests of northwestern Europe. Very easy to distinguish from the others. Now, what I'm going to talk to you about in the rest of the lecture, having given you that brief introduction, is I want to talk mainly about Roman glass and glasses derived from Rome. The chemistry of these things is quite complicated, so I thought if we focused on examples of one particular type of glass or one particular period, that would probably be easier to follow. Okay, so here's our chronology. Plant ash glass, Near Eastern plant ash glass, starts off all over the Mediterranean. Well, starts off in the Near East, but it spreads over the Mediterranean in the late Bronze Age. And this carries on until around 800 BC or something of that sort, when natron glass starts being produced from Egyptian natron. And you see this marked change in composition. In Iraq and the East, they go on using that material. But in the Mediterranean, it goes over almost completely, and in Western Europe, to natron-based materials. Potash glass doesn't come in until the around 900 or 1000 AD. Okay, so the first case study I'd like to discuss is the Portland vase. This is probably the most famous piece of ancient glass. It's in the British Museum. It was discovered in around 1500 or thereabouts. Its previous history is not well known. And it's basically a very dark blue glass with a white frieze, which is decorated with figures. And those, the interpretation of the frieze has been interpreted in about 40 or 50 different ways. There's a large number of interpretations. There's a lot of discussion about it. Now, what this brings home to us is that glass is not always transparent. Ancient glass is often opaque and often strongly coloured. It was seen as a kind of semi-precious stone. As you can see with this, it imitates a cameo stone. And that was really the situation until the middle of the 1st century AD, when colourless glass became much more common, when people started blowing it into bubbles and shaping it in the way we know glass workers do today. Anyway, the Portland vase was came into the British Museum in its early days, and in the 18th century, it was very, very of great interest, considered to be of great interest as an antiquity. And Josiah Wedgwood, the potter, in 1769 started making copies of it. And of course, you'll be familiar with these ornaments and knickknacks and flower pots made of plastic, which are still basically derived from the Portland vase. People keep your grandmother probably has one with a flower pot or something in it. Now, the Portland vase has been subject to a history of breakages and restorations. And that, from my point of view, as someone who likes a sample to analyse, is not without its disadvantages. And one of the things that came up with the vase was the subject of its date. Although it's generally been assumed to be Roman in origin and dates were around the late 1st BC, early 1st AD, people have always suggested that because it was discovered in the Renaissance, it might be the work of Renaissance glassmakers in Venice, where they were extremely skilled. And I thought that when I analysed this some years ago, I'd shown that wasn't the case. But then, I think in 2003, an article appeared in this art historical magazine, Minerva, by the editor, whose name is, I think, is Jerome K. Eisenberg, who claimed it probably was Renaissance. And I was upset because I thought that years ago we'd shown it was Roman, but it didn't stop the newspapers reproducing this. For example, this is from the Times of London, saying that the Portland vase is the work of a Renaissance master. So it gives the analysis actually gives us a chance to try some dating on the glass, because you've seen how the composition of glass changes with time because they use different fluxes and they use different colorants and sands and so on. So when a student, I have to say it was a student apparently, visited the museum in 1845, he picked up a stone object and smashed the vase into about 150 pieces. And here you can see them laid out after the breakage. It suggested he was drunk at the time. One can only hope that was the truth. But anyway, when the vase was restored, there were some leftovers, some tiny fragments which weren't put back into place by the restorer. And even though it's been conserved on several occasions since, these tiny fragments of glass have never been put back in. And that gave us the chance to find out the composition of the Portland vase. We only need 1.2 millimetre of glass to do this. When we have to break the object deliberately ourselves, we'd make a tiny scratch on the corner of a shard of glass and snap off the corner. And then we can examine that in a scanning electron microscope. And there on your right, you can see a sample in the SEM. It's about 2 millimetres across. And what you notice is that there are two colours, or two shades of grey in the image. This is the dark blue, almost black glass in the background, and this is the white glass on the surface. And this piece actually allowed us to get an analysis of both types of glass on the vase. And here's a close-up of that sample. And what we found was that the dark glass was coloured by a small amount of cobalt, which makes glass blue. It doesn't take very much to make it a very strong colour. The glass bottles you see in chemists and pharmacists, or at least you used to see in chemists and pharmacists, maybe you see them in reconstructions of 19th century chemists and pharmacists, they were all coloured with cobalt. Cobalt is still the colourant we use today to colour glass dark blue. And the reason the white glass is not transparent is because it's full of these tiny particles you can see on your left there, just here. And they're tiny particles of a compound called calcium antimonate. And it's the crystallization of those particles in the glass when it was heated that makes the white opaque. And this is typical of Roman glass, but also it's typical of glass in other periods as well. For example, in the Renaissance. And here's the full analysis of the two glasses, the blue and the white. A whole series of elements down the sides, but the ones I want you to focus on are the magnesium, just there, and the potassium, just there. And you'll see they're both very low, below 1%. Now what this means is that the source of alkali was natron, pure sodium carbonate, not plant ash. Now, when we look at the Portland vase in terms of the change in fluxes, we can see that if it's made with natron, it puts it kind of in the Roman type period. Okay, it's a long Roman period, but between about 800 BC and 1000 AD, that's when this flux was used, whereas the Renaissance glass would lie somewhere in here. So this seems to show that the Portland vase is Roman, not Renaissance. And just to emphasise that, we took sherds of Roman cameo glass from excavations and Venetian glass from shipwrecks and compared the Portland vase with the two. And you can see that the Portland vase not only lies in the right part of the diagram for Roman cameo glass, but it lies right on the curve. So it's clearly fully consistent with the Roman glass composition. And the big noise made in the newspapers about it being possibly Renaissance was quite wrong. Okay, the next application of this sort of technique of dating glass is going to be medieval. It's going to be medieval enamel, but it has a Roman twist, and I'll explain that to you in a minute. And the sorts of enamels I want to talk about are Romanesque, early 12th century, made in the Rhineland, or the Valley of the Meuse. And these colours, the colours on these plaques, are coloured glass on a base of copper. And the copper has been gilded, so you can see the gold surface there. The glasses are opaque. If they were transparent, you'd get the horrible brownish shade of copper showing through. And this is an example from the British Museum, and that's because I worked there for 25 years, and this is one of the projects I worked on while I was there. And the reason we did this project originally was because the enamel specialists in the museum were hoping to be able to show that different plaques with slightly different styles came from different workshops, and they were hoping that the composition of the glass enamel changed from workshop to workshop, so we'd be able to assign the enamels to the different workshops. Now, the way these things are made is shown on your left there. Basically, you take a plaque of copper and you engrave it, and then you put powdered glass into the cells you've made by engraving the copper, and then you push it slowly into a furnace to about 800 or 900 degrees, and you watch it, and the glass fuses, the glass powder fuses and fills the cells. And when you notice the glass glowing, you pull it out of the furnace quite quickly, because if you don't do that, the whole thing could spoil. You could damage the metal because of the high temperature. And so we've got these coloured glasses in the enamel. Now, We can take minute samples. You can see there's some damage in the corner on the large plaque on the right there. And in the plaque on the left, there is a blown up image of a corner. And so you can usually ease out a very small piece of enamel. Now, since I did this work in the 1980s, late 80s, early 90s, non-destructive techniques have been developed to the extent where we probably wouldn't have to take samples to get the same answer. But we needed a sample then. And even now, you still get better analyses by taking a small sample. So, here are the fragments of glass. At the top right, you can see 6 small fragments of glass in the scanning electron microscope. They're around 1 millimetre across, so they're really very small. And then, moving across, also at the top, you can see the piece on the right there. And here we are. You can see this is that one. And you can see it's quite blotchy. And those blotches, those patches in the glass, are the original fragments of glass which were crushed. They were put in the cell, then they were remelted, but they didn't completely fuse together. They just softened and stuck together. And so you can get some idea of the grain size of the powder, the glass powder they put into the cell. And this little, down here, there we are, this scale bar here is 1/10 of a millimetre across. So that's the sort of size of powder they were putting into the cell, the glass powder. They crushed it to around 1/10 of a millimetre. And this is 10 times higher magnification. And you can see these particles, these white particles, are calcium antimonate, the stuff which makes the glass opaque. And the base glass, in between the calcium antimonate particles, is a soda lime silica glass with low magnesia and low potash, and it's a natron glass. And this looks like a Roman glass in these enamels dating to the 12th century, to about 1120 AD. Now, if we put it in context, there it is, it lies on the natron trend there, but it dates here, and it's completely off the end of, if you like, the period in which we think this glass was being made. So what's it doing on these enamel plaques? Well, Theophilus, who was a monk who wrote in the early 12th century about how enamels were made and a whole lot of stuff about metalwork and glass making and so on, he tells us what was going on here. He says different kinds of glass, white, black, green, yellow, blue, red and purple, are found in mosaic work in ancient pagan buildings. And by pagan, he means Roman, and he's talking about Roman mosaics. These are not transparent, but are opaque like marble, like little square stones. And you can see some pictures of these tesserae, these little cubes, glass cubes from Roman mosaics. And Theophilus says enamel work is made from them. And so as late as the 12th century, the craftsmen were collecting their coloured and opaque glass from old Roman buildings in Europe to make their enamels. And one is familiar, if you visit churches in Rome, for example, you'll be familiar with the occurrence of kind of precious Roman stone in some of the mosaic work, the floor work, the cosmati work on the floors. Imperial porphyry, for example, the purple stone is used. And if you look carefully, you can see, if you go to the Vatican, you can see that some of that is round, and they've cut pillars in order to get the stone to make the mosaic in medieval times. And they were still selling Roman stone in Rome for ornamental work in the 18th century. So here we've got an example where they were using old Roman glass in the same way in their craft work. Now, of course, the implication of this for our study was quite disappointing, because although we've shown something very interesting and we've fitted our work with a well-known medieval text, which was very satisfying, in fact, it meant we couldn't possibly identify different enamel workshops from the composition of the glass, because in fact they were all using old Roman glass, which is a relatively homogeneous composition. And when you compare the composition of blue glasses from the medieval enamels with blue glasses from Roman mosaics, here's a list of elements there. You can see they're almost exactly the same, whereas the medieval window glass, which is made from potash lime glass, is very, very different. Okay. Now I'd like to move on to looking at provenance and distribution of glass. And I'm going to talk about the Roman glass tradition, as I said. Natron-based, based on this alkali from Egypt. They use sand rather than quartz pebbles as their source of silica. And we know that because of the impurities in the glass. That's what they were doing. And this was a very large industry. And it's often not appreciated just what a scale this industry operated on. These are the baths of Caracalla in Rome, 3rd century AD, major public building. And a study by Delane, a kind of architectural archaeology, she worked out that there were 16,900 meters squared of glass mosaic on the vaults of the building and 3,400 meters squared of window panes. And that works out about 300 tons of glass. And this is just one building. It's quite an easy calculation to do. You know, it may be 250, it may be 400. People come up with slightly different numbers depending on how you think thick the average window pane was or the mosaic was. But that's the sort of scale that one is dealing with in a large glass production, a large building project. And Constantine's Basilica, 4th century at CReA, again, windows, lots and lots of windows, presumably had glass in them, and a very large amount of glass. So not only do we have the vessels, which of course as archaeologists are often the things we're most familiar with because they have shape. If we get window glass, it goes into a box marked window glass and we can't really do much else with it. But vessels, yeah, we can do something with those, so we don't pay a lot of attention to the window, but it means that you needed glass making on a large scale. Now, the traditional model of how they made glass in the ancient world is basically this one. And this was the model which most people worked to until around 2000, until around 10 or 15 years ago. Natron from Egypt, the source of soda, and then a glass workshop like this medieval one you can see on your left, and this is a Bohemian manuscript dating to around 13 or 1400. Somewhere close to the workshop, they'll have had a source of raw material, a source of sand. That workshop would melt its sand with ash, or as far as most people felt about Roman glass, with natron. And each workshop would have its own source of sand, and that would mean that each workshop produced glass of a distinctive composition. Now, this is quite important because it affects everything you do. It really brings home how model-dependent our thinking is. Okay? Because, of course, people then thought, okay, if we analyse glasses of different shapes or slightly different colours, we should be able to identify these different glass workshops. So, maybe you can tell the difference between glass made in Brussels and glass made in Leuven, for example. However, it didn't work out like this. And, it's pottery thinking. They're basing their thinking on pottery. Form fabric groups. To glasses of different shape have characteristic compositional fingerprints which correspond to different workshops. And that would teach us a lot, if they have, about trade, about local trade and the way vessels move. And some really good work was done, I'll show you in a minute, by some people called Baxter and Jackson. So this is the typical Roman glass composition. I'm sorry, the PowerPoint slide seems to have slipped slightly in transport. But basically, it's soda lime silica glass, as we said. The soda comes from natron. The lime and the silica actually come from sand, as you'll see. And then there are a range of minor elements, including potassium and magnesia, but also iron, which is what makes the glass often a pale blue colour. And so Jackson, Baxter and Cool, not necessarily in that order, in a couple of papers in Archaeology in 1995 and I think 2005, carried out a major study of glass vessels in England from the 1st century AD to see if they could identify different workshops. And these are just two elements, for example. And although we've got a kind of group sticking out over here, you'll notice that each of these sub-diagrams really looks very, very similar. And these are cast bowls, these are facet cup beakers, these are wheel cup beakers, and these are cylindrical cups. And so the composition of all these different vessels is more or less the same most of the time, which means that you can't apply the model we just saw. You know, we'd expect them to be different. If you're looking at terra sigillata and amphorae, for example, you expect them to be different in composition in terms of their clays. This doesn't apply in this case. Roman glass is very, very homogeneous in composition indeed. And that situation prevailed until the early 90s, when our attention was drawn back to this. This is a big slab of glass in a cave in modern Israel, in a Byzantine cemetery, as it happens. It's a big glass slab. It weighs about 8 tons. Its dimensions are 3.5 meters by 2 meters, and then it's about 0.5 meter thick. And it was excavated in the 1950s, I think, but the first kind of scientific report or archaeological report was by Robert Brill in 1964. And at that time, he said, this is the 3rd largest piece of glass known to man, after the reflector on the Mount Palomar telescope and something else. I can't remember what else it was. But, you know, even in the 60s, this was a really large piece of glass. And there it was, sat in a cave. The excavation had never been written up. All the debris, and we assume the furnace from around it, had been removed. And it just sat there like this. And by a great coincidence, somebody walked into my office and said, I've just been out to Israel and I've met this archaeologist who has this amazing site with glass-making furnaces on it. And here you can see a picture of the site. It's a place called Bet Eliezer. It's near Hadera, close to the Israeli coast. And down here, you can see the archaeologist concerned was a lady called Yael Gorin-Rosen, who I'm still working with. You can see these flat areas, and each one of those flat areas has got tiny fragments of glass in the base, and each one of these was a furnace to produce one of those big slabs, like the one we saw from the cave, just a slide or two back. So they had 14 furnaces. Each one of them could produce 8 tons of glass. So this is quite a large amount of glass. And when Brill originally discovered the Bet Sherim slab, he said, you know, actually what I think they were doing is they were smashing this slab up, or they were intended to smash it up, to break it up with hammers and then distribute the glass. The broken glass could then go to glass workshops where people were blowing glass, and they could make windows and vessels in those workshops. And on this site, with these big glass furnaces, we've got chunks of glass about fist size, but we don't have any sign of blowing or working into vessels or windows or anything. This is what we call a primary glass production workshop, where they're making the original raw material. And this is more or less how it worked, we think. This isn't so clear, but actually there are two fireboxes just down here, shown on this plan, just there. The fires were lit in here, and then what happened was the heat went up to the roof of the furnace, was reflected down and melted the glass. And actually, at almost the same time, everything came together at once. We were on we had a kind of meeting just after these were discovered by Yale in Israel, and on that trip was a Dane, a guy called Torban Soda, and he was out looking at the ethnography of bead making in India, and they came across a furnace where they were making 3-ton slabs of glass in India. So all of a sudden we had the archaeological evidence and we had ethnographic evidence, ethno-archaeological evidence for the production of glass on this scale. And I should say that since this time, Marie-Dominique Nenner, who's in Lyon in France, has been working in Egypt, and she has glass making furnaces which will melt 20 tons of glass, dating from the Roman period. We have a site in Tyre in Lebanon, which it looks as if one batch was possibly as much as 30 tons of glass. So these were making really large amounts of glass at one time. And they weren't blowing it themselves, they were specialists in making the raw glass from sand and soda. And so the theory then kind of developed that they were probably doing primary glass making in the east. Here's the east coast of the Mediterranean, and what you can see here is I've kind of marked natron, the source of natron, down near, not so far from Cairo, only 50 kilometres away or something. And then we think they were using the sands around the coast of the Mediterranean. They made slabs. They broke them up into lumps just like these, and these lumps are now very, very apparent in shipwrecks, not only in the East Mediterranean, but off the coast of France, around the Mediterranean. They turn up everywhere. It's like it was an artifact that people didn't understand before, so they just poked it away in a corner, in a box. But now we understand what's happening. They're very important evidence. And then those broken fragments of glass were transported all over the empire to make vessels and windows. And even on this scale, if you think about the building such as the Baths of Caracalla in Rome, that would have kept that glass-making site at Betelgeuse going for a season or two to produce the amount of glass needed. So even so, the consumption of glass was extremely high, and we certainly haven't got to all the evidence for the primary production yet. So why were they doing it here? Well, partly because the natron is in the southeastern Mediterranean. Natron's quite a difficult material to transport by sea because it's soluble in water. So you don't want it to get too wet because it will just disappear. So the theory is that they worked down there because of the soda, but not only because of the soda. The sands on the east coast of the Mediterranean are very, very good for glass making. Pliny, Strabo, Josephus all mention the sand from the mouth of the river Belus, as it was called then, in the Bay of Haifa, as being an important source of sand for glass making. And this is probably why these are analyses of sand from the Israeli coast, which I've replotted from the report by the geologist. And I'll just explain to you what this means. So over here we have the south, and over here we have the north. The blue is calcium carbonate in the sand. Now that's shell fragments. If you look at sand on the beach, you can see these little white fragments of shell in your sand, okay? And you need lime, you need calcium carbonate to go into your glass to make it stable. And then the red line is the colour of the sand. The higher, the darker. And the darker it is, the more iron in the sand, and iron colours the glass. Just as iron makes our terra sigillata pottery red, or our handmade pottery sometimes dark or grey, iron, even a small amount of iron, will colour glass blue or green. But in the Bay of Haifa, where the Beluz River emerges into the ocean, into the Mediterranean Sea, you can see that the amount of iron in the glass, the red, is particularly low. And actually the calcium carbonate content at around 20% or 18 or 19% calcium carbonate is just the right amount to produce a glass with about 8% calcium oxide in, which is what we find. So it seems that these beach sands were particularly suitable for making glass. So is this model correct? I mean, we've got the theory, we've got the ethnoarchaeology, we've got the archaeological evidence of the furnaces. Can we show it applies to the archaeological glass? So here are the implications. You have a small number of primary glass makers, and their glass is going to correspond to the composition of the sands. But each one of these primary glass makers supplied a large number of workshops. Okay, I've shown two because that's what I could fit into the diagram. My skills with PowerPoint aren't that brilliant. But actually, one of these primary factories was probably supplying tens or hundreds of small secondary glass production workshops who were shaping glass. The same glass making source can supply a large number of workshops. So you're not going to be able to tell the difference between them very easily by chemical analysis, because they'll all be based on the same glass. And in some cases, individual workshops would use the same glass, but in other cases, a workshop can receive glass from more than one source. So sometimes we might see a whole series of workshops in an area, all making, or indeed in a region over the whole of Western Europe as it happens, all making glass from the same stuff, and then just occasionally, or from now and again, one workshop will have two different types of glass because they're being supplied by two different workshops. Now, the nature of that supply is a matter, we haven't really looked into that in great detail yet. How's it done? Obviously, there wasn't a regular contract between factories and workshops. There must have been some sort of trading network. So the first thing we did was we looked at composition of glass in the first millennium AD when they were using this natron-based raw material. And rather than look at Roman glass in the strict sense, we looked at glass which was slightly later, late Roman to Byzantine glass in the Near East, because it did look slightly more variable. And we were able to identify a number of different glass groups based on the composition of sand that was being used. Now, you can see these on a graph, but in real life, these groups aren't very different. Okay, this one, for example, where are we? This one averages out at about 8% calcium. So does this one. This one has 2% aluminium, and this has 3%. So it may be just a difference of 1% or so in one component allows you to tell the difference between the primary glass-making workshops. Most of these analyses are done on raw lumps of glass. And the yellow points down here are from Bet Eliezer, which is the archaeological site I showed you with the tank furnace bases in it. And there are a number of other groups. We suspect the pink group there is from the Wadi Natrun, but actually, or we suspected it then, but it looks as if that may not be the case. So even then we were speculating. And we decided to look at the glass at a site called Moroni Petraea on Cyprus, because that was quite close to the coast of Israel, where they were making glass in tank furnaces, but it was separated by the sea. So we figured that, glass made on the Israeli coast would probably have been taken to Cyprus without being recycled or remixed or remade into vessels and then moved around. We thought there might be a direct connection. So that was one of the first places we looked at, in a church in Cyprus, where the glass was used for lamps and vessels. And when we looked at trace elements in these glass groups, we can see that different glass groups not only have different major element patterns, but sometimes can have quite different trace element patterns. So you can see the blue and the red one are different there, for example. There, that's the dark blue symbols and the red line for trace elements, and that's the light blue symbols and the blue line. So you can see that we have a range of different kind of elements where we can see maybe clearer differences than we can from the major elements. Okay, so here's the glass from Mardi Petrera, from this site on Cyprus. Most of it corresponds with this dark blue area in the centre of the diagram, which is standard glass from tank furnaces in Israel, dating to around the 6th to 7th century, from these large what we call tank furnaces, where they were making the glass. And the Mardi Petrera symbols are in red, and you can see that most of those correspond to what we call Levantine 1, which is the kind of key, the first glass we really recognise as being made on the coast of Israel and being distributed quite widely. And some of them lie down here. Let's see, okay. Nope. There we are, just there. And that's another group, I'll explain it a bit later, which we call HIMT. So it looks as if we've got two glass groups at Moroni, but when we look at the trace elements, we can see that the major group, which we call Levantine 1, corresponds to a range of glasses from sites in Israel, from Bet Eliezer and from Apollonia. So it looks as if raw glass was going from Israel to Cyprus. Now, the other type of glass in that group is called HIMT. Now, this is an incredibly widespread glass which comes in and around the 4th century AD and lasts for a couple of centuries. It's called HIMT because it's got high iron, manganese and titanium in it. Here's a typical glass, and HIMT is different because of these elements here. It's very distinctive. It has quite a deep colour. It's the main sort of glass used in Western Europe after about 350 for a century or so. And it's also quite widespread in the Mediterranean as well. And that glass, there we are. Here's the Moroni samples. There's the majority down in the Levantine area there. Here's the HIMT, and you can see the remainder of them are this HIMT type. So Mardi Petrera seems to have been receiving glass from two sources, or it has the glass in the vessels in the church made from glass from two sources. One is our Levantine 1 source, which corresponds to the sort of coast of Israel. The other one is this HIMT source. We don't quite know where this is yet, but that seems to be the category of glass you have there. So this overall kind of matches up with our kind of production based on big primary glass furnaces on the east coast of the Med. Now, we have to figure out the origin. We want to figure out the origin of this HIMT glass, this other one. We don't know where it comes from. We need to know. Now, trace elements we've looked at, but they don't actually fingerprint where something is coming from. There's some work by some people in Germany, Hans Vederpol and colleagues. They have a type of glass which is very close to HIMT, maybe identical in composition, which they think was made in Germany in the 4th century. It seems unlikely that the HIMT at Moroni was made in Germany. So we're going to isotope studies, and particularly in Belgium, Patrick de Griese in Leuven University has been doing quite a lot of work with isotopes. And there are two elements which are useful in the study of glass: strontium and neodymium. Now, neodymium is the sort of element that, unless you're interested in the kind of interiors of mobile phones, you won't be very familiar with. It's what's called a rare earth element. It's quite rare, but it occurs in glass maybe 10 or 20 parts per million at very low concentrations, but it is quite distinctive as to the origin. Strontium you may be more aware of, because strontium is an isotope, or has isotopes, which we use to trace the origins of people. For example, in the Neolithic and the Bronze Age, you may remember Ozzy the Iceman in the Alps. Well, work's been done on his teeth to show where he came from. And you can use strontium to identify movement. Unfortunately, neodymium is in such low concentration in the bones of people and in teeth that you can't measure it in order to get this information, but you can measure it in glass and in stone artifacts. So let's have a look at why these work. Well, strontium is associated with lime, with calcium. Sr, strontium down the bottom there, and Ca are both alkaline earth elements, and the main source in glass, they either seem to come from shell or from limestone, which was incorporated in the sand. So strontium, we know what we're looking at. That's probably telling us where the sand came from. But how? Well, this is the strontium isotope ratio determined by geologists of ancient ocean water over geological time, from 500 million years ago to quite recently. Not apparently relevant archaeologically, but actually modern seawater is just up there, 0.7092. So beach shell has this particular unique number. Limestones are always down here. Beach shell is up there. So if our sand was beach sand and the lime in the sand was shell, then we would expect it to have this ratio, this 0.7092 ratio. And that allows us immediately to see if our glass was made using beach sand or inland sand. There's another alternative, which is the possibility they crushed shell and added it to another sand, but I don't propose to discuss that at the moment. So, here's glass from these furnaces near the coast of Israel. The strontium isotope composition of these shell fragments in the sand, 0.7092, and that's just the ratio we get in the glass from those furnaces. So they're using the local beach sand to make the glass. That's their raw material. Here's a diagram showing the strontium isotope ratio along the bottom against the strontium content of the glass, for glass from a series of furnaces. These are the Palestinian coastal furnaces. There's modern ocean water. They appear to be mainly shell. We have some glass made in inland furnaces in Egypt, which plots down here. And we have some glass made with plant ash, some slightly later Islamic glass, the green symbols over there. So it seems to be quite a good discriminator. Now the second isotope we're dealing with is neodymium. This is slightly more complex. What this map shows is the neodymium isotope ratios of sediments in the Mediterranean Sea. Here we go, -12, -11, -10, -9, -8, -7. You can see that the isotope ratio changes as you go from west to east. And as you go from west to east, it becomes less negative or more positive. So the values over here in the sea sediments are kind of -3, -4. And the red symbols, the red numbers, are the values from the tank furnaces. So they're slightly contaminated, we suspect, with stuff, with material coming in from the land, but basically they seem to suggest that this sort of pattern is consistent. So, if we're looking at glass vessels, which are made from sand in the Western Mediterranean, we'd expect these very low -10, -11, -12 values. If we're looking in the Eastern Mediterranean, we'd expect the values to be much higher or much less negative. Why is this happening? Well, it's all to do with the River Nile, okay? The River Nile comes down from the highlands in Ethiopia and Kenya, where there are volcanic rocks. It carries, or it used to before they built the big dam in Egypt, but it carries vast quantities of sediment down to the sea. It's washed around the sea like this, and basically all the sand on this coast is derived from the Nile, or the vast bulk of it. And because the sand is rich in these volcanic rocks, which are quite young, it has the same kind of isotope ratio, neodymium isotope ratio. So you're carrying sand round here, which is contaminated essentially by volcanic rocks with very, very low isotope ratios. Or sorry, high isotope ratios, less negative isotope ratios. So that's what's happening there, and it's all down to the geology. And here we go. You can see it, there it is. Gives you a high epsilon ND. Now we can use that to look at things like the HIMT glass and decide if it is from the Eastern Mediterranean or not. And here are the values. So on your right, under the yellow titles, you can see HIMT glass from London, from Egypt, and from Tunisia. And on the right-hand side, you can see the ratios in the tank furnaces in Palestine. And you can see the numbers are more or less exactly the same. And so what this seems to suggest, is that the sand used to make HIMT glass was Eastern Mediterranean, and even in London, that glass is the raw material being used to make vessels. The strontium, I don't show the numbers, but the strontium suggests it's probably beach sand. So what they were doing is they were making this HIMT glass. It's quite low quality, it's green, it's got high iron, it's not terribly nice, but they were making vast quantities, presumably it was quite cheap for that reason, and then exporting it all around the Roman world in the 4th, 5th centuries and beyond. Saxon glass in Britain, Merovingian glass in Belgium and France have a very, very similar composition. Okay, so that kind of shows the kind of long-distance distribution of primary glass. Now I'd like to move on to secondary glass working. What goes on in the workshops? And there are a number of things we want to ask. First thing is, you want to know what the source of the glass material was. And we've got some indication of that already, how we will approach that from these isotopes. We want to know whether it was fresh or recycled glass. We know that people recycle glass on quite a large scale. They're bound to. It's a very recyclable material. Apart from copper, there's probably, and lead, I guess, there's no material which is as easy to recycle as glass. We want to look at the scale of the activity. How long were the workshops active for? We want to know about the glass workers. You know, is someone making glass in Britain, which is right on the edge of the empire and where I come from, have they got a permanent workshop there? Or are they glass workers who travel around the empire and then make the glass where they stop? What were the identities of the glassworkers? Are they like to be British? Are they like to be French? Are they like to be Greek? All those things can be of interest, and they're the sorts of things we should be able to tease out, or many of them. Identity is a bit more difficult, but you can get some clues by analysing the glass. So the glass workshop I want to look at is one I'm working on, or have been working on quite recently, which is in Basinghall Street in London. 2nd century CE, 2nd century AD. It was excavated by Museum of London Archaeology in 2005 as a rescue excavation. And one of the important things about it, as far as I was concerned, is that we had 2 glass specialists working on the finds, and they sorted them out in terms of type of find, shape of vessel. As far as one could go with visual identification, they processed these glass finds. The workshop is just there. This is the modern day Bank of England. It's right in the city of London. Here's the Roman wall. Here's the fort. There's the forum just down there. The amphitheatre's just there. And it's in something called the Walbrook Valley, which is a river valley where quite a lot of industries were located in the Roman period. There's leatherworking, there's pottery making and so on, all in this one area. And word of warning, this is the excavated area, and this is the area which was rich in glass making finds. And you can see that actually it's only part of the deposit in terms of glass working. The rest of the glass working site has not been excavated. It was only this area which was being where there was redevelopment going on. And the finds are also good from this workshop, which makes it quite exciting from my perspective. I mean, this is not a cheap project. I have to say, this cost £15,000 just in terms of the amount of analysis we did, not including the write-up and so on. So as we're looking at this as a kind of case study, you need to be aware that it's great to do this, but you have to choose your cases carefully to make it worthwhile. And this was a good one because it had actual fragments of glass from the furnace. There was a big fragment of glass just here, a big kind of lump about this size, weighed 30 kilograms, still there. And these are fragments from a tank furnace down the bottom here. Here we are. This one here, it's a layer about 20 centimetres thick of glass, which appears to have been in a tank. Now, that immediately brings to mind the tank furnaces we saw in Israel. But we don't think they were making glass from raw materials here. In fact, on Roman glass-making sites, there's very little evidence for crucibles or pots in which they make glass. They seem to have worked quite often from tanks. Smaller tanks, not the big 8-ton ones, maybe ones containing half a ton of glass or even less. But that seems to be frequently what they did. And this is a reconstruction by Mark Taylor and David Hill, a couple of guys who do experiments in Roman glass making. This is their reconstruction of the furnace. The big piece of glass here, they interpret, and it seems absolutely to be right, to be a failure of the furnace, the glass pouring out of the furnace when the furnace failed. The layers seem to suggest slow cooling. For example, this one has got greenish glass at the top, bluish glass in the middle, and then the bottom has got these spheres, these white spheres, which is where the glass cooled very slowly and crystallized. So this seems to be the last glass in the furnace, which was never worked because the furnace failed. And then the furnace failed, they poured out glass from the end, and then they just seem to have abandoned it. They didn't recycle it as one might expect, reuse it. And there's quite a lot of evidence here. There's chunks, lumps of glass, angular lumps of glass, which come from the furnace, and some of those might be raw chunks being brought in to the furnace to supply it from the east. We don't know at this stage. There's a lot of vessel glass. There are different colours. There's not only blue-green glass, which is the typical Roman colour, or indeed dark greenish glass, which is this layer on the top of the furnace, which seems to have been exposed to the air and have cooled very slowly. But also there's colourless glass. The Romans were quite good at producing colourless glass, and there's some here. But also the other thing we've got are moils. Now moils are kind of little cylinders of glass, just a centimetre or two across. And I think I have a slide, explaining them. These are moils. Now, the moil is the glass which is left round the blowpipe when you blow a vessel, okay? You blow the vessel, you crack it off the blowpipe, or take it off the blowpipe, and then you're left with a ring of glass around the blowpipe. If you put the blowpipe, it's hot, it's an iron blowpipe, into water, the moil falls off. So we've got a large number of moils, and they're particularly useful. And we didn't realise how useful they were when we started this project, but they are useful because actually one moil is equivalent to one vessel. So each moil is equivalent to a vessel. We don't have the vessels anymore because, of course, they were given to the customers, to the consumers, but we do have the moils. And it's become increasingly apparent as we did this particular project that if you analyse moils, you can get a much better idea of what went on at the workshop, and rather than analysing the lumps and the chunks, the amorphous stuff, which is largely what we did, and you learn by experience, of course, unfortunately. So that's moils. At the top there, there's partially fused window glass. This was probably brought in as cullet. Cullet is glass which the glass makers are going to use to remelt, to recycle, to make new glass. So we have evidence for cullet, we have evidence for vessels, we have moils, we have glass from the furnace. This is a fairly exceptional glass working site. And the typical Roman workshop actually used 3 types of glass, as far as we can see. By far the most abundant is green-blue glass. Pale blue, not unattractive, but it's obviously blue. It's not a deep blue, it's a pale blue. And this was obviously the common glass they used for containers, for bottles, for a lot of windows, and so on. But there are 2 categories of colourless glass. In order to decolour glass, which has got iron in, you see it's all got about 0.5% of iron in it, and iron colours the glass. So what they did 2 things. They either added manganese, and that tended to pull the iron into a state where it was less coloured, or they used antimony, SB, down there. That's antimony, which is even more effective at making the glass colourless. So you have these 3 categories of glass: green, blue, colourless 1, colourless 2. As you can see, apart from that, they're more or less the same. They're all soda-lime glasses. More or less the same amounts of potassium, magnesium, more or less the same aluminium, slightly lower aluminium in this one, but in general, you know, for years and years, we saw no difference between them at all. And what emerges from this is that there are probably at least 2 different sands. The antimony decoloured glass, shown on the graph as the yellow squares, is different from the blue-green glass, this one, and the manganese decoloured glass, which is kind of in between this and this. This is the really good antimony decoloured glass. It looks slightly brownish now because it's got weathering on the surface. It's been in the ground. But actually, it was almost as good as a modern drinking glass. If you get a fresh piece, it's really impressive. They knew what they were doing in a purely empirical way. They didn't understand the chemistry, of course. So we have 2 sands. Were they coming from different regions, different places? Let's have a look. Here are the isotopes for these 2 different colours. The blue-green glass is shown in blue symbols. The antimony decoloured, the really good white glass, is shown in white symbols. And the manganese decoloured glass, most of that is from these points are from Jerusalem. Everything else is from London. The manganese coloured glass is over here. And what we can see is that the neodymium and strontium isotopes in the blue-green and the colourless glass, the antimony colourless, the really good colourless glass, which looked different in that elemental diagram, had different slopes, are almost identical in terms of their isotopes. They're both Eastern Mediterranean coastal sands. So the stuff is coming to London from the Eastern Med, even the white and the blue-green glasses. So were they bringing new glass from the Levant, or were they using recycled glass in this particular workshop? Sometime glass from the Levant must have got to London, but it's quite possible that they were just recycling old glass which had come from the Levant. And what was the time span of this workshop? Well, recycling. We know the Romans did it. Marshall in Epigrams tells us that sulfur matches were bartered for broken glass. So you took out your broken glass to a guy in the street who was collecting it, and he gave you a sulfur match or sulfur matches in return. And Statius also tells us. You can see in the top right-hand corner there, somebody in modern Lebanon, in Tripoli, sorting out glass for recycling. And there are baskets of glass to be reused. Now, we don't know how careful they were at sorting out the different colours of glass, but we have Roman glass vessels with blue handles, with green handles. Inevitably, some coloured glass is going to get mixed in when you recycle it. If you go to the bottle recycling at your local supermarket or wherever it is here, you'll try and put your bottles into the recycling bin some days, and you'll find the brown bin is full up. So you have to put it in the bin for the white glass. Or the green bin is full up. So you put it in the bin for the brown glass. And what you're doing when you mix these colours is you're contaminating the glass you're using. You're adding different elements which aren't normally in the colourless or the brown or the green glass to that glass. And that gives us a trace, a fingerprint of recycling, which we can use to good effect when we're looking at the glass. One of the most characteristic elements is cobalt. We saw that in the Portland vase. It made the Portland vase blue. Cobalt in sand is incredibly low, just a few parts per million, 4 or 5 parts per million. If you just mix a couple of shards of cobalt blue glass into a bin of white glass, you'll see the difference. It will bring the cobalt concentration up. And you can tell that contains recycled glass. Okay, so how do we tell the difference? Well, this is what we've been doing. We've been looking at the elements associated with colour. Copper and cobalt are obvious ones. Copper makes the glass green, cobalt makes it blue. Lead goes in with antimony, which makes it opaque. Zinc goes in with copper. Silver goes in with copper and lead. And we find that fresh glass from tank furnaces has got relatively low concentrations of these elements. But glass which has been recycled has quite high concentrations. So we can tell that these glasses contain recycled material. Now, I would emphasise that it's quite difficult, in fact virtually impossible at the moment as far as I know, to work out how much recycled glass there is there. As a general rule of thumb, we tend to think that the more of these elements that are present, the more recycled glass is present, but we can't put a number to it at all. And so this is an indication of recycling. And so we can use these recycled elements to try and reconstruct the life of the workshop. Because imagine if you're working in a glass workshop, you have some recycled, maybe you're using some old window glass to blow your vessels, okay? You blow the vessels with that. You then run out of glass window. You've got to get some more glass. You send off a boy or a young person, I should say, in order to collect some glass fragments, and they'll come back with another batch of window, perhaps with some different colours in it, some old vessel and so on in it, and the trace elements in that recycled batch will be different from the trace elements in the first one, simply because the amount of coloured glass included in it, the amount of recycled glass, is slightly different. It's from a different vessel, it's from a different place. And in this way, we can track what's going on in the workshop. And this is what seems to have happened at Basinghall Street. Here's tin and lead, both of which are indicators of recycled glass. Now at Basinghall Street, there's a batch of glass down in the bottom left-hand corner, and that comprises chunks, the broken lumps of glass. It has moils, which are the rings from the blowpipes, and that appears to be fresh glass brought in from the east, and vessels, the moils which represent the vessels from that fresh glass from the east. And then you've got these other groupings on the diagram, and that seems to be the first campaign of melting. Here we go. What they do then is they bring in cullet, and these yellow points, and this is where I wish I'd done a lot more analysis. You know, you really wish when you're doing something like this, you'd done 100 rather than 50 or rather than 20 analysis. You can never do enough. But the yellow glass is cullet. It's window glass and vessel glass collected from London and brought in to be remelted to make more new vessels and windows. And this centre group down here is virtually everything else. It's those big slabs, the lumps, the moils, the green layer at the top of the furnace, that all concentrates in this area in the middle, and we think that's one campaign, one season, or 1 week, maybe one month's blowing. And it looks as if this glass furnace had perhaps just two phases of operation. The first one, where they blew the glass with the fresh glass from the east down here, and then when the local population had got interested, they collected cullet, windows from old buildings, most likely, and then they started on a second campaign, and that's this one here, and the furnace failed. We had that big lump which poured out from the end. We've got the layers and so on, and we think that was the last time they did it. So they may have used the furnace just twice. There's another suspect item over here, which is another moil, which is just suggestive that they might have blown and had another session of blowing, or session of melting, from mainly from cullet, but that's the only one we have. It looks as if there were just 2 phases in this furnace, which really means that the furnace was probably used perhaps for just a few weeks, couple of months or something like that, and then the glassmakers abandoned it. It broke, they didn't bother to rebuild it. On the edge of the empire in Britain, they weren't getting a lot of fresh glass in from the east. There weren't that many buildings, old buildings to take the windows from to use as cullet, and once they'd used it up, they left. They stopped making glass there, and maybe for 10 years, maybe for several years, we don't know. And this suggests to me that these glassmakers were peripatetic. They were travelling around. They probably came with their cargo. They came with the glass vessel, the raw glass in the first instance. Then they exploited what cullet they could find, and then they went on to somewhere else. So here we go. This is a short-lived workshop. They bring in Syro-Palestinian glass in the form of chunks. The first campaign is mainly fresh glass. Then they bring in local cullet. Then there's a second campaign, and the furnace fails. The glass workers just go. There's not enough glass to justify them staying. Now, where they joined the cargo of fresh glass from the east, we don't know. That would undoubtedly have travelled to Britain by boat, through the Mediterranean and up round the coast. So it's feasible that they came from the east. But because there is a difference in general terms in glass forms between east and west, it's much more likely that they got onto the boat somewhere in the western Mediterranean, maybe on the coast of France, when it was coming up towards Britain. And that you can get quite a lot of information. We're teasing quite a lot of information out of these glass workshops now, but it's much easier when you're living on the edge of the empire. If you've got vast quantities of, imagine trying to do this in Rome, where vast quantities of glass are being made. We'd have so much noise. All our groups would blend into one another. We wouldn't be able to tell what was going on very easily. But out here in the West, it's not so difficult, because glass is a rarer material and we can get more resolution, more clarity about what was going on. Now this idea of glass being a kind of a relatively unusual and relatively rare, glass making being a relatively rare or relatively unusual activity, is also confirmed by looking at the consumption of glass through its chemistry. And this is a case study we did at a place called Stony Grange. This is a Roman, Roman settlement, I suppose, in eastern Britain. You can see it on the map, just down there. It was excavated by Ralph Jackson and Tim Potter back in the 1980s. And basically the site consisted of a large stone building, you can see it over here, and a small attached settlement of wooden houses, of wooden buildings. The stone building has a hypocaust, it has mosaics, it has glazed windows. So it was quite an important building. It was kind of presumably some sort of Roman administrative centre controlling the agricultural activity in the region. And then you've got this densely occupied area over here. Now, the glass vessels at Stony were examined by Jennifer Price, who's a very, very well-known glass specialist. And I mean, this emphasises more than ever the importance of having really good typological control over the material you're analysing. It's not just enough to analyse glass. You need to make sure you know what the types are. And 58 glass vessels were retrieved from Stony. Several hundred unidentifiable, very small fragments. And this is typical of glass because, of course, when it's abandoned on site in the site formation processes, people are walking around, they're treading it into the ground. A lot of it just breaks up. But we analysed the glass vessels which were identifiable by form. And one of the major groups, you can see in the figure there, these are cylindrical cups with rims which haven't been cut off or broken off. They're fire rounded. So if you kind of if you cut a glass in order to make a flat rim, you'll get a relatively rough and sharp surface. But if you do it while the glass is hot, or you reinsert the glass into the furnace, the rim will round. So this is quite a diagnostic feature of this particular type. And of this group, of the 58 glasses, we had at least 14 vessels made in this particular form. So they're very, very coherent typologically. There were 17 fragments, but Jenny reckoned there were 14 vessels. And also we had a couple of colourless glass jugs, drinking jugs. Or pouring jugs, I suppose, rather than drinking jugs. Now, this is the analysis of all the glass we did from Stony. It's about 30 or 40 samples. I can't remember exactly how many. But basically, it falls into 4 quite tight groups. There are cups down here. There are yellow-brown vessels just there. And our cylindrical cups are this group just here. Okay? They're very, very discrete. Now, when you can compare the spread in those groups with the spread of other glass. So, for example, this is the composition of glass from 4 of those big tank furnaces in Israel, and each tank furnace is indicated by a different colour. So the yellow glass is all from a single furnace. The purple glass is from another furnace. Look at it spread. The blue glass is from another furnace. And then you compare it with how tight that group of glass from Stony actually is in terms of its compositional spread. And here is a comparison with cylindrical cups from a number of different sites. And once again, you see, although they're the same form, they're quite spread out relative to the cups from Stony, relative to these cylindrical cups. Now, what that means is that these cups are from a single batch of glass. They're from a single pot, probably, or tank, or whatever they were melting the glass in. They were all melted at one time. The glass was heated at the same time, it was homogeneous, and each glass came out with almost identical composition. And I have to say that for anyone who's interested in analysis, the spread in those red points on the diagram is the analytical uncertainty in our analyses. So basically the red points, each one of those vessel fragments is exactly the same composition. And this is a single batch of glass. They represent a single pot, and it was a set. This set was acquired on site at one time by one person. Probably one person commissioned the glassmaker to make that glass. We don't know if it was made on site at Stony or if it was made elsewhere and brought in a wooden crate or something, but clearly those cups were made at the same time. And when you look at the distribution of the cups on site, this is what you can see. This is the big stone building over here, okay? And over here, these are the roads. Here are the wooden buildings down here. And what you can see is that that most of the black points, and each of those black points represents a single cylindrical cup. Most of them are concentrated in one area of the site. So this particular batch, this particular consignment of glass wasn't used in the high status building, although it's a significant proportion of the assemblage. It was used in these wooden buildings over at the back. And this gives you some idea of what it might have been ordered for and why it was being used. Remember, there are a couple of jugs here as well. And so we think this is a drinking set. And it's telling us about the function of probably the building where they were found. There's probably a taverna or a refectory or something of that sort over on that side of the site. And that's what these vessels were being used for. And the way the glass appears to be distributed in these individual groups indicates that procurement, the obtaining of glass, was punctuated. Only at certain times did glass come onto the site. So instead of being confronted with 200 years of glass vessels kind of spread out, what we can see is what we have on this site is maybe 4 events where glass came onto the site in those 200 years, and that's all. Glass was much less available than you might think from the initial impression. It's telling us something about value. And it's telling us about ownership as well, because it means that the glass was owned by a single individual or group or authority. Someone ordered that glass for a specific purpose. And that's consistent. If you look back to our workshop in London, it's the same sort of picture. Glass is not going to be a regular, everyday material. Glass workers come in, they make vessels to commissions or to sell. The glass goes out, then they go away again, and no one obtains any glass, maybe for the next few years, maybe for 10 years. So, to sum up, Roman glass making. Okay, I've given you a number of sort of cases where we're trying to tease apart what's going on with the structure of this industry. Large tank furnaces in the Eastern Mediterranean. Patrick de Vries, who's done a lot of analysis, virtually not all of the glass is analysed, but maybe 90% of the analysis he's done all indicate Eastern Mediterranean origin for the glass. Almost all of the blue-green glass seems to have come from the Eastern Mediterranean. Some of the colourless may come from elsewhere. It was traded around the empire in chunks, and then you've got large numbers of individual glass workshops, some peripatetic, particularly on the fringes of the empire. Centrally, you'll have permanent workshops where the glass is shaped into vessels. In Britain, we have a punctuated glass-making situation where we have peripatetic glass workers, and the supply of glass is completely dependent on these people. They reuse windows and vessels, but even so, you have to have windows and vessels to recycle in the first place. So glass, in Britain at least, was a relative luxury. Okay, I'd like to finish there, so if there are any questions, I'll be very happy to answer them.